Hey guys, this is a follow-up to the Intro to Calculus average rate of change video. So we're going to focus more on instantaneous, but still a little bit average. Okay, so let's just talk about rates of change using equations. Okay, so we talked about determining the average rate of change and how that relates to it being like a secant. We talked about the instantaneous rate of change and how that's like the tangent to a line. So let's just write some formulas to start off with. I think that's where I wanted to start. So let's just say we have this graph like this. And let's do our classic, potentially quadratic function, but we don't know. So let's just write the things that we learned from the previous video, but a little more formally. Okay, so we have this function. Let's call it y equals f of x. It could be any function. And let's say we have a point down here, point P, and we have a point up here, Q. Let's talk about the average rate of change real quick from the previous video. So we defined this as the change in y over the change in x, and it's equal to y2 minus y1 over x2 minus x1. So let's just, because we're going to be using different notations throughout the course, let's just get comfortable using different notations. So I'm going to call the x values A and B here for now, and I'm going to call this one f of A because it's the y value at point A, and I'm going to call this guy f of B because it's the y value at point B. So point Q here, I'm just going to write it on the other side. So point Q, if we did the coordinate, would be B comma f of B. And point P would be A comma f of A for the xy coordinates. So if we wanted to write that as a formula, average rate of change, we would be subtracting our y's divided by B minus A. So that's the average rate of change. It's also the slope of a secant. Like so. Okay, sorry, I have a hard time drawing that, but anyways, so that line is our secant, and that's average rate of change. Okay, let's say we're talking about instantaneous rate of change. Then we're still talking about the change in y over the change in x, but we talked in the previous video about how we want the points to be as close together as possible. Like we want this stretch to be really small. So if this is our function, and we say this is point P and this is point Q again, and we use all the same things as last time, except this time I'm going to describe this interval that we want to be really small as, I'm going to call it H. That's the distance between the x values in P and Q. So P, sorry, I'm just changing location. So P is at the x value of A, and then we'll just call this x value A plus H. It's some distance away from A, but we want it to be really small. Like for example, if A was 3, then we want this to be like 3.00000000000 an infinite number of zeros 1, for example. So if we had to write that as an equation, we would write, we would subtract the y values, so f of A plus H minus f of a would be our y values, and then our x values would be a plus h minus a. If you take a closer look at the denominator, if we end up collecting like terms, it's going to turn out to just be an h on the bottom. Right? Because the a's are going to subtract and go to 0. So this formula right here is going to slightly change, but for now, it looks like this, and it's called the difference quotient. And it is how we can calculate the instantaneous rate of change at a point. So like at point P, we're going to use a super small value. We're going to reduce that so it's so tiny, it's almost nothing, so that we're able to approximate the instantaneous rate of change at point P. So we're getting closer and closer to figuring out kind of like being able to do instantaneous rate of change so quickly. So this is going to lead into kind of a definition of derivatives pretty soon. And since we're using the Nelson textbook, it actually jumps the gun and it gives it away. It kind of tells you right off the bat that the slope is equal to the limit, which you don't even know what that is yet, as the change in x approaches 0 of delta y by delta x, or change in y by change in x. So it's kind of saying like as this interval right here, as this interval gets to 0, so as the denominator approaches 0, then that's going to give us the slope of the tangent. So how we can write that is we can say the limit as h approaches 0 just means that we want this to be really like pretty much 0. We don't want it to be 0 because then we'll be dividing by 0. But as it approaches 0, what happens with these values? So f of a plus h minus f of a divided by h. So this is like getting quite far ahead of ourselves. But this, and we should also say if the limit exists. I feel like you might be like super confused about what are limits. Limits are just like as you approach something, what's happening. So as this interval is getting smaller and smaller and smaller, so as Q is approaching P and this interval is getting smaller and smaller and smaller and smaller, what's the rate of change becoming? So that's kind of what a limit is. But we're going to do a whole week of limits next week. So you don't really have to concern yourself too much, other than the fact that to stay focused, we're trying to find the slope at point P, and we want our 2 points to be super close together. So pretty soon you're going to see this thing called first principles, but not quite yet. In the future, you will totally see this referred to as first principles, but for now, it's just the slope of a tangent line. That's all it is. Okay, I haven't done any practice questions yet, but I might just stop the video right there and I'll do some examples on the next video.